Okay, so real quick, those of you who turned in the mini exam last time, I think there were only 3 of you. I did go through them and kind of grade them, but I wanted to try and meet with you all if you have time, because there were a few problems on there that I think were just kind of, I don't know, I didn't want to take off as much as I would take off. So I think if we can sit down and talk through it, I might give you a little more time to think through the problem a little bit more. So I'm available tomorrow in my office hours, but then I'm leaving out of town on Wednesday. So your exam is Wednesday. I told you you're gonna have a proctor, right? Were you on a bike today somewhere off Westover Hills? Okay. I was with my daughter taking her to school, and I was like, I think that's my student. Okay. It's cold.
Just a little bit.
Okay. Anyway, so Wednesday's the test. So if you're one of those 3 people, you can come in tomorrow, or we can wait till after spring break. No rush on that, okay? Otherwise, I'll just grade it and give you the grade back, whatever it was, okay? Sorry, Milton, that I didn't have it posted.
I'm just worried now.
Yeah, I mean, it wasn't anything big. It's just like, if you miss one problem, then there was only, what, 4 or 5? So it's a big deal. So, all right. Okay, we are going to continue today with new material, and at the end I might talk a little bit about the test. I talked about the test last time at the end of class, but now I have a better idea of what I'm asking, so we can talk about it at the end, maybe last 10 minutes. This is a quick review of what we've done so far, the main ideas last few classes. If we have a function of 2 variables, we're trying to find the max and mins, right? That's the whole idea here. So if we have a function of 2 variables, which gives us a surface, if we're trying to find local max and min, which means we're looking on its entire implied domain, we're looking for the little, hills and valleys, then what we do is we calculate that capital D, which was a formula, right? And we just compare those and see which one gives us, the what do you call it? Like that second derivative would give us like concave down and up, and if it's positive, we do one thing, negative, it's something else, right? So that's what we do if the function is defined on its implied domain. Now, if we restrict the function to a closed bounded region, then the steps are a little different. That's what we did last time. We do like the first part of this, which is to figure out where the partials are 0. And anywhere where the partials are 0, we kind of hold on to those points. And then we would have to move along the boundary, and that's where we would have to, L1, L2, and do all that, and then it would turn to a Cal 1 problem. And then once we got where those had maxes and mins, we just kind of compare them all and pick out our max and our min, and that would give us the highest and lowest values of our function bounded on that closed bounded region. All right. Today we do one more thing that's related to this, and that is what we're going to be trying to do. It's kind of like this right here. We're going to be trying to find the absolute maximum and minimum of a function, but not on a closed bounded region, just basically on a curve. So you know how when we had the closed bounded region, the whole idea was like, if you look at the domain as being on the ground, if that was closed and bounded, then that would map up into some surface up here. You would have you would kind of have like what the image of that closed bounded region was into the surface, and we were trying to find like the absolute max and min up here. Today, we're just going to be trying to find a more efficient way to find the max and min just on the boundary. Okay, so that boundary is a curve, isn't it? So imagine just taking the points on the curve and plugging those in. You would get this curve up here, wouldn't you? So we're taking out the middle now, this center region. We're taking it out. We're just looking on the curve. Can we find the max and min? Make sense? But to do that, we have a whole new approach, and it's somewhat difficult to explain. I have a visual explanation of it, but it's not a proof in any way. But I hope it'll help you help convince you of where it comes from, or like where the formula I'm about to give you comes from. So let's first take a look at that. This is a visual representation of the formula that you're about to get. And just so you know, the name of this section is called Lagrange multipliers. And that's what we're going to be doing, all right? What is that? What?
I love my name tag. Yeah.
Oh, okay. I was like, okay. I thought there was something about Lagrange that was funny. I think you'll you won't laugh after we have to do a couple of examples. All right. So here's the idea. All right. So you know how I said what we're going to do is we are going to look at like the closed boundary region on the ground. Just look at its boundary, right? Just its boundary. Okay, I want you to look at that as that boundary on the ground. I want you to look at that boundary right there as being what we're going to call a constraint, okay? All right, so imagine, if you will, that I always have a hard time with this. Let me get you the boundary. Okay, I'm gonna use this picture to get you a boundary. Right now, do you all see a surface? Yes, I'm going to call this g of x, y. All right, that is some surface. It's a function of two variables, right? Now, if I were to set this equal to, let's say, a number like I'll use 2 for now. Then what this is doing is it's saying, remember, this is your z, this is your z, this is your z output. So this is saying where on this surface is your z coordinate 2, all right? And wouldn't that correspond to just like this ring around this thing, like something like this? Wouldn't that be where that surface is held constant? Make sense? We're all right with that? Okay, so if I look at this as a function of two variables, if I hold it constant, then I get this ring right here. Now, we all know what the gradient of a function is, right? The gradient, we did this a couple of classes ago. The gradient of a function of two variables is just a vector, and it is the partial derivatives of that vector with respect to x and y. So the gradient of this g, of that right there, is the vector. It's two-dimensional, partial of g with respect to x, partial of g with respect to y. Right? That's what the gradient is. What I'm having the computer do right now is I'm going to have the computer calculate the gradient vector for that surface. Okay, so I'm going to kind of come up from the top here and take a look down. Can you all see that vector right there? You all see that green vector? It's two-dimensional, right? So it doesn't have a z component. If I look at it straight from the side, you can tell it doesn't point up or down. So it's just two-dimensional, just pointing straight out, right? And that's the gradient of g. And the gradient of g, if you remember, one of the most important things is that that direction is the direction that I would need to start walking if I wanted to go up on the surface the fastest. So can you imagine that if you were on this ring, on that green ring, that if you started to walk in this direction, I don't know if I'm going to be able to get that back up there. I won't. Okay. If you were to start to walk in this direction, you would have to start going up the surface. Do you all see that? And so that green thing is telling you which way to start walking in order to start going up the fastest. Now, if I move around, if I start to move around, it doesn't matter. I can go to different points on that ring. That gradient vector will change depending on where I am on that ring. Are we all right with that so far? Okay, all I'm going to do now is I'm going to take that ring and I'm going to drop it down to the xy plane, and I'm going to drop that vector down to the xy plane. All right, so it's everything that we had up here. I'm just projecting it down there just so we have it. All right, and now what I'm going to do is I'm going to take this out, I'm going to take that ring, that vector, and that ring out. So now you know where this is coming from, right? We have some surface. We have some surface that was set equal to a constant. We computed its gradient, and that's the picture we have, right? Okay, now let's take some other function, f of x, y, right? Some completely different function. Now, when I put it up here, it's going to look kind of like g, but it's not. So here's this new function. Now that's not g, here's g. G's that one, there's f, all right? Now what I'd like to do is I'd like to take just these points along the ring and map them up into this surface. And when I do that, I get this blue curved looking thing. So if you look at it straight from the top, can you see that those blue points came from that green curve, just mapped up into the surface? Got me? Now I'm going to compute, or no, let's look at the max and min points. So right there, let me pull this out just a little bit. Can you see on that blue curve we have a max there, a min there, and a min there. Do y'all see those? Okay. Now I'm going to compute the gradient of f. Okay, so now I'm looking at the gradient of f. And that's the partial of f with respect to x, partial of f with respect to y. All right? Got it? And so along f, along this curve, if I start moving, let me start moving somewhere. Okay, do you see that this blue vector, if I look at it from the top, is not necessarily the same as the gradient of g. Can y'all tell that these aren't necessarily pointing in the same direction? If you can't tell, I've done them down here in two-dimensional space so you can see that they're different. Can you see that? Yeah? Okay, now watch, something amazing is going to happen here. As I start to move around, I want to go to where we have a minimum. Okay, we have a minimum right here, see that? I'm going to just move around there, and I want you to look at the gradient vector of f and the gradient vector of g, and tell me if you notice anything. They're parallel. So look, this is the picture on two-dimensional space. Do you see that where we had a minimum, the gradient of f, this one is the gradient of f, oops, and the green one here was the gradient of g. Do you see that they're parallel? That's not a coincidence. It's actually a property of functions, all right? If you take a function and you restrict it to where another function is constant, I know that seems weird, but wherever another function is constant, let's just for the sake of you understanding what this really means, what if I replace this with something? X squared plus y squared equals 2. Isn't that just a circle, radius 2? So what we're saying is if I take a function, a surface, and I restrict it to this equation, just that circle being mapped up into it, then wherever this has maximums and minimums, the gradient vectors are parallel at those maximums and minimums. Now I'm going to go to a different maximum, or to a different point. Let me move to where we have this maximum, and just I'll make this a little smaller. Keep an eye over here in two-dimensional space. What happens to the green vector and the blue vector? The red vector don't worry about, but just keep an eye on the green and the blue. So I'm moving around here. So we are definitely not at a maximum, right? We're right here. And notice that these vectors are not parallel. But as I move around and get myself up to that maximum, I have to take one more little step here. Boom, right there. You see that? We're parallel. That means these are scalar multiples. Remember, that's what it means to be parallel when you talk about vectors. They're scalar multiples. And I can keep going. You know, I can go to the next one, and it's again going to happen. There we go. You can see that they're parallel, right? And so that is what Lagrange multipliers is all about. The formula I'm about to give you, I think, will make a little more sense now, hopefully now that you've seen the visual of it. Let me show you the formula and see if we can see how that connected to that picture. So here it is. Again, I'm not sitting here like trying to prove to you why it's true. All right, that was just a visual to show you, yes, this indeed does happen. Right, the proof is a little, I don't think the book even goes through a proof. So it's beyond the scope of this class. All right, so this is what I was telling you like when I first started class. We already know how to do a couple of things. We now develop a very powerful method for finding the maximum and minimum values of a function subject to some constraint. So here it is. Given a function of two variables, subject to a constraint, g of x of y equals k. So there's our equation in two variables. Maybe it's a circle, maybe it's a line, who knows what this is. This is some constraint. Then here's how we find the maximum and minimum values. We just need to figure out where those gradients were parallel, right? Wherever those gradients are parallel is where we're going to have a max or a min. So what we do is we take the gradient of f and we set it equal to not the gradient of g, but a scalar multiple, right? Because remember we said that they had to be parallel, which means they need to be scalar multiples. So this is lambda. So we're trying to figure out where the gradient of f is equal to some constant times the gradient of g. And not only do we need that to be true, we need to make sure that the original constraint equation is true, which means we need to make sure we're on the circle, or whatever it is, that curve, or whatever curve is on the ground. We've got to maintain the fact that we have to be on that, but then these have to be parallel, these two vectors. Make sense? We have to do an example. So what we're going to do is we're going to evaluate our surface at all the points x, y that we get from this set right here. Okay, so whatever x's and y's satisfy these two things will now be tested into the function, and that'll give us, the values, and we'll know it's biggest or smallest by just comparing, right? All right, so now this is still the notes, all right? This is still us trying to figure out how we're going to go about this. So let's break this down. If I want to figure out where the gradient of f is equal to some constant lambda times the gradient of g, that means this is the definition of the gradient of f, right? And then this is what lambda times the gradient of g means. You just distribute the lambda through to both components, right? And so for two vectors to be equal, we have to have the components match. So I need this component to match that component. That's the first equation. I need this component to match that component. So that's my second equation. And then remember, we have to have the original constraint equation is maintained also. So that gives us a third equation. So if you notice from this, we'll have we'll have three equations, right? Three equations, and we'll have three unknowns. The three unknowns are x, y, and lambda. Those are the things we don't know, right? I don't know what x is, what y is, and what lambda is that make all three of these true at the same time. So we're solving a system of equations. Here's the bad news. It's three equations, three unknowns, but those equations are not necessarily linear equations. So you cannot use linear algebra, you can't use matrices, you can't do any of that. So you have to figure out another way. And so this is going to be a lot of algebra to try and get this to work. All right, let's do an example, because there's nothing like an example to help make this all make sense. I have a surface here. So this is actually the example that I showed you in the very beginning with my little animation. This was what I was trying to get. I have a function of two variables, here it is, and I'd like to just constrain it to this right here. That's a circle of radius 1, right? That is. So what we have is the surface we're trying to find the maximum and minimum of. Here it is. We are constraining it to the circle on the ground. We are imagining mapping this circle into the surface to give us this curve, right? And then we are trying to find those points. There should be 4 of them total, right? 2 places where we get max and 2 places where we get min. Does it all make sense, visually at least? Okay, let's set up the problem then. Let's do the work. All right, so here's what we need. we want the gradient of f to be equal to lambda times the gradient of g, and we want g of xy to be equal to k. That has to be, those are the conditions that we need to meet, all right? So this is going to allow us to set up 3 equations. Here's the first equation. First equation is that the partial of f with respect to x must equal lambda times the partial of g with respect to x. So this is that breakdown that I showed you in the previous slide, right? We need that equation to be true. What's the second thing we need? Partial of f with respect to y must be equal to lambda partial of g with respect to y. And then what's the third condition that must be met? G of xy must be k. Okay, so now let's start filling this in, right? What is the partial of f with respect to x? So you go up, here's f, right? Oh, you know what we should do? We should probably identify what g of xy is. What is g of xy? It's this piece right here, right? That is your g of xy. And then equals this side, which is your constant, right? Right? Okay, so your partial of f with respect to x is just 2x. That must equal lambda, and then times the partial of g with respect to x, which is 2x. So lambda times 2x. So that's our first equation, right? Second equation, partial of f with respect to y. 4y times lambda equals times lambda partial of g with respect to y, 2y. And then what is our constraint equation? Well, it's exactly what's written up there, right? So now, our goal is to find any x's, y's, and lambdas that make these 3 things true simultaneously. Okay? So you have to find an x, y, z. It's almost like we're trying to find an ordered triple, except that the lambda isn't part of a graph or anything. It's just those 2 are on the ground, aren't they? Those are like on that circle on the ground. The lambda is something else. It's not, it's just the scalar that makes our gradients. It's the constant in front of the gradient of g that makes these things parallel. So don't look at lambda as like a z value. Is that all right? But we're still trying to find 3 things, x, y, and z. I mean, x, y, and, I just said it. X, y, and lambda. All right, here we go. Algebra time.
Number 1, you could divide by 2x.
Okay, so number 1, I could divide by 2x. Now, I think I mentioned that that's dangerous in here. Did I not mention that?
Yeah.
That is, because remember, if you divide by x, 2x or whatever, then you have to promise me x can't be 0, right? So why don't instead we bring everything to one side, all right? So I'm going to bring everything to one side. 2x minus lambda times 2x equals 0. And now factor instead. And if you do it this way, you won't lose a solution that way. So what do I have? I can pull 2x and I get 1 minus lambda equals 0. And so we know right now for equation 1, there are 2 potential solutions, right? 2 potential solutions. Either x equals 0 or what?
Lambda equals 1.
Lambda, I put y. Or lambda equals 1. Y'all with me? All right. So, shall we work through number 2 and just see what 2 gives us? Let's just see what 2 gives us right now. Do the same thing here. Move everything over to one side. Factor out a 2y. So we get y is 0 or lambda is 2. Okay. And this one, you can't really solve it for x or y because it's 2 variables, 1 equation. All right, so how are we going to do this now? Remember, you have to find me an x and a y and a lambda that make all 3 true at the same time.
You could try every, all 4 possible combinations of one of the conditions number 1 and one of the conditions number 2, and see if any of them will give you an x equals y equals 1.
Yeah, so I think this is what you're saying. You have to go through these, like logically. You have to say, okay, let me take the first consideration, which would be, what if x is 0, okay? Let's say x is 0. So I'm going to start, this is going to be kind of like separate work here. I'm going to start by saying, let x be 0. Now, if x is 0, what can I say? Yeah, equation 3 would imply that 0 squared plus y squared would have to be 1, right? And that would mean that y would have to be plus or minus 1, right? You take the square root on both sides. So far it looks like this. As an ordered triple, if x is 0, I could get y is 1. And if x is 0, I could get y is negative 1. Does that make sense? Now, we still would need to figure out what lambda would have to be in this case. Because, well, you don't need lambda for your final answer, but we're going to get into a habit of finding all of them, x, y, and lambda. So let's figure out what would happen in each of these cases. Remember, this is x, this is y, this is lambda. So let's say if x is 0, y is 1, what does lambda have to be? And where are you going to get that from? Yeah, so looking at this case right here, if y is 1, then equation 2 would imply that, look, if y is 1 here, you get 4 equals, what is that? I can't think, 2 lambda, right? If y is 1, then you get 4 equals 2 lambda, which means lambda is 2. And so that would force that to be 2, right? Make sense? And then what would happen on the next one? What if y is negative 1? I'm running out of room. If y is negative 1, equation 2 again, right? Would imply that 4 equals negative 2 lambda this time? Because you're replacing this y here. No, sorry. It would be negative 4, wouldn't it? Sorry, negative 4 would be equal to negative 2 lambda. So lambda is still 2.
Couldn't you also look at the, where you got y equals 0 or lambda equals 2? Can you also look at that and say, since y is not equal to 0 in either case, lambda must be 2 in both cases?
Wait. If you mean when I was trying to figure out what lambda was here,
Yeah.
to say that what?
Since y is not equal to 0
Uh-huh.
in each case, lambda must be 2 in both cases. Because
In order to make that, now why is y not 0?
because either 1 or negative 1.
Pardon?
Because it's either 1 or negative 1.
Okay, so
Those two.
we have to, you're on the, yes, what you're saying is true. I want to make sure everyone understands where we got lambda from this way, only because in a little while we're going to do functions. This function is going to be a function of 3 variables. This is going to be a function of 3 variables, or an equation with 3 variables, and then it's not going to be as easy to just look and eliminate. We're going to have to like algebraically go through each one. This stuff, it gets real tedious because you start to lose track of where you are and what you're doing. Okay, so I'm trying to make it as systematic as possible. All of this, the entire thought right here, everything that I put down on paper, is all under the assumption that x was 0. If x is 0, here's the result. Do you all agree? Okay, now let's take a look at the next possibility. I could do lambda as 1 now, couldn't I? Okay, let's do it. I have to do all 4. Oh, let me write those down. What did we have? We had 0, 0, 1, 2, and 0, negative 1, 2. All right. Now, let's let lambda be equal to 1, because that would be this case, right? If lambda is 1, is there anything I can get from this? Okay, so from equation 2, what would we have? 4y is equal to 2y. And in this case, if you subtract 2y from both sides, you get 2y is 0. And that means y would have to be 0, wouldn't it? And once you know that y is 0, you can go to equation 3, and equation 3 would then tell you that x squared plus 0 squared must be 1, so x must be plus or minus 1. See that? So if lambda is 1, equation 2 forces y to be 0. Once y is 0, equation 3 forces x to be plus or minus 1. And now I can say that I could have 1, 0, 1, or negative 1, 0, 1. X, y, lambda. X, y, lambda, right? Make sense?
Yes.
So now I have 2 more. How many should we have? Do you remember on the picture how many max and min places we had? Yeah, we had two places where we had a max and 2 where we had a min. And those are 4 distinct points, aren't they? Okay, so let's see. What should we consider next? We've taken care of this. I should maybe also state when we put x is 0, then we were satisfying equation 1, right? And then to satisfy equation 2, we did this, and then equation 3 being satisfied. So all 3 were satisfied, right? Let's go to the next thing. What would be the next thing we need to look at? Let y be 0, right? So that means that equation 2 is satisfied. Now this is going to go fast now because we've already looked at y equals 0, haven't we? If y is 0, equation 3 tells us that x has to be plus or minus 1. We've already done the work on that, right? And so aren't we back to those 2 points again? We're back to these. We could go solve for lambda again, but we would still get 1. We're not going to get different lambdas at the same point. We're always going to have the same lambda. So can we just stop here? Say we're done here? Okay, done, because we've done that already. And the last thing I need to consider is letting lambda be 2. So if lambda is 2, equation 2 is satisfied. And then what can you do? Go to equation 1, plug in 2 for lambda here. Okay, so let's do that. Equation 1 would imply that 2x is equal to what? 4x, replacing lambda with 2. Subtracting 2x on both sides would force x to be 0. Right? And once x is 0, you go to equation 3 and get y. And we've already done that, haven't we? We've already looked at this case. Now, you could have also, when you said lambda is 2, you could have just looked over here and said, hey, I already did that, right? I already did that. But again, I'm trying to get you to see what you have to do is, the problem that students have with this is that they go and they run through like one scenario and they get all the things right, but they don't consider all the other scenarios. And so they get like, maybe they get one of the, one max or one min, but they don't get all of them. Does that make sense? Okay, so we've gone through everything. That's it. We've done this, we've done this. And so those are the points. So I want to find the max and min values, right? Right now, I don't know what the max and min values are. So what I need to do is take these x and y coordinates and plug them into the original function. So I need to find what is f of 0, 1, what is f of 0, negative 1, what is f of 1, 0, and what is f of negative 1, 0. And let's just, you see how I'm not using the lambda, right? Just using the x and y's. So what's that first one? What's f of 0, 1? We're plugging into f. 2. 0, negative 1? Same thing, right? 2, and then 1, 0? 1 and 1. So what is our maximum value? 2, right? What's our minimum value? 1, right? So if I go back and I look at this curve, this blue curve here, I know that the highest value I reach, right, is 2. And the lowest value on that curve is 1. And I can even tell you where they occur. Like I can look at it from the top. And I can tell you that that maximum is going to be at 0, 1 and 0, negative 1. These are our two maxes. Our two mins are over there. Make sense? All right. That's it. That's Lagrange in a nutshell. Let's do another one. So take a look at this one. Is that the same problem? Hold on. Did I accidentally make a typo there? Is that the same problem? Are we doing the same problem twice? Now you have an inequality, right? That's different. So what we're doing now is we're saying our domain is not a circle on the ground, it is a disk on the ground. It's everything in there, right? And we're mapping all of those points up into the surface, which actually gives us some weird shaped region here, right? Instead, that green, instead of the blue curve. And so what we're trying to do is find the max and mins of this. Now look, we still have those two maxes, don't we? But do you see that we have a min down here? This is our min now. It's not these two anymore. Get it? So how do you think I can go about this? Well, how about this? Well, no, not that. That's not what I meant. How about this? Why don't we do the exact same thing we just did? Okay? So we do the Lagrange. Dot, dot, dot. We do all that. And we get our f of 0, 1 equals 2. F of 0, negative 1 equals 2. F of 1, 0 equals 1. F of negative 1, 0 equals 1. All that was us going around the boundary, right? Just around that outside. How do we take care of the inside? Well, just think back to what we started with when we started talking about max and mins. Couldn't we find, hilltops and valleys by just setting the partials equal to 0? Right? And that did not care about domain at all, right? So if we go back and we use that same method, so we're going to do this along with now setting the partial of f with respect to x equal to 0 and the partial of f with respect to y equal to 0. We need these to both be true at the same time. So let's do that. Partial of f with respect to x is 2x. That must be 0. Partial of f with respect to y is 4y, must be 0. And these have very simple solutions, don't they? X is 0, y is 0. And so the only point that we have is the point 0, 0. Right? Now, do I go calculate D, capital D here? No, because I'm not trying to figure out if this is a local max or local min. What I've discovered is that there's something interesting happening here, right? Something interesting happening here. And I want to compare that to what's happening along the boundary. But I also need to make sure that this point lies within our domain. So is this inside that disk?
Yes.
It is, right? Because that disk this is in here, right? So if you plug in 0, 0, you'll get 0 is less than or equal to 1. That's true. So this point does live in our domain. So all I need to do now, since it's in domain, meaning that x squared plus y squared is less than or equal to 1, we just need to figure out what the value of the function is there. So what is f of 0, 0? 0. And so now, this is our minimum, and 2 is our max. It happens at two places, but I can tell you now that if you take this surface and you constrain it to that disk, then the biggest value you're going to get is 2, and the smallest value you're going to get is 0. So you see how it's like blending two things together here? You've got the Lagrange you have to do along with this part. All right, can I keep going? Another example. Find the maximum and minimum values, or find the maximum and minimum of this function with this constraint. Looks like we're restricting something to a circle again, aren't we? We're taking these points that live on this circle, on the edge of the circle, we're mapping them into this thing. What is this? If we were to graph this, what would it look like? A plane, right? Because these are all linear. X to the first, y to the first, and remember this is z, isn't it? So this is like z equals blah, blah. So you have an equation with x, y, and z. They're all raised to the first power. If I graph that f, it's going to be a plane. So can you all imagine what this might look like? You have a plane. Maybe it's, it's tilted somehow. Taking points on a circle, plugging them up into the plane. You should get something probably looks like an ellipse or something on that plane, right? You're trying to find the highest and lowest points. So what do we need? 3 equations, right? 3 equations to be true. First equation, partial of f with respect to x must equal lambda partial g with respect to x. Second equation, partial of f with respect to y must equal lambda partial g with respect to y. Third equation, the constraint g of x, y must be equal to k. So we'll always start these this way. All right, what's the first equation become? 4 equals lambda times 2x, right? Partial of this with respect to x is 4. Partial of that with respect to x is 2x. Just don't forget your lambda. People always forget their lambda. All right, partial of f with respect to y is 6 equals lambda. Partial of g with respect to y is 2y. And then our final equation is just the constraint equation. And so there are our equations. Now, because these are just numbers, I'm just gonna divide both sides by 2 here, and over here I'm gonna divide both sides by 2. We don't have to worry about dividing by a constant. We won't lose any solutions that way. So there we go. Any ideas? Any suggestions? Any idea of how we can find an x, y, and lambda that are going to make all of this true? So be careful. I'm only saying this because I've seen it happen. When you say that 2 equals lambda x, this does not mean that x equals 2 or lambda equals 2, right? We all know that, right? This only works if that's 0. You can't set them both equal to 2. So that's no go. Any ideas?
If you divide one of the variables over, so like say you get 2 over x and then equals lambda, and you plug in that lambda to the other equation?
So you mean solve this one for lambda,
Yes.
and then take that and plug it in here?
Yes.
You could do that.
Or could we set them equal to find x and y and plug it into, like,
Solve this for x,
yeah. And
solve that for y,
plug it
and then plug both of those into here, and then you'll have just lambdas in there? Is that what you're saying? Yeah, you could do that too. So there's several ways you can go after this. That's what makes this a little bit weird, is that students can take different paths to get to the solution. Let's go with, I kind of like the idea of solving this for x, solving this for y, and then taking those answers and plugging them in there. Not that solving for lambda here and then plugging that into there wouldn't work, but let's just think about what would happen. If I solve this for lambda, and then plug it in here, I'm going to have an equation with x and y in it, right? And then what I'll have to do with that is solve one of them for x, or solve it for x or solve it for y, and then plug that in there. So I think in the end it's all going to be the same sort of thing. All right, let's do this. Now watch what I write here. Super important that you understand the next step, because this is what gets you to lose credit on things, on problems. Okay. If lambda is not 0, then equation 1 tells us that x is 2 over lambda, and equation 2 tells us that y is 3 over lambda. Do you see that it's very important that I start this by saying if lambda is not 0? Because after I finish this and figure out what the hell's going on, I then am going to have to ask myself, what if lambda had been 0? Okay? So we first say, look, to be safe with the algebra, to be able to define x and y legitimately, dividing both sides by lambda here means lambda can't be 0. So I start with that. Now, what does equation 3 give us? So equation 3 tells us now that x squared, which would be this, right? 2 over lambda, that quantity squared, plus y squared, which would be 3 over lambda squared, must be 13. And now this is a single equation with a single variable. The single variable here is lambda, isn't it? So let's go ahead and square everything. We get 4 over lambda squared plus 9 over lambda squared must equal 13. Any ideas on how to go about this now? You can combine these in one fraction because they have the same denominator. So 13 over lambda squared equals 13. Multiply both sides by lambda squared. 13 lambda squared. And then that means 1 equals lambda squared, which means plus or minus 1 equals lambda. So just algebraically, we just solved for lambda. It can be two possible things. Y'all good with that? Now I need to continue here. Okay, so I'm continuing, but I'm running out of room. So I'm going to continue right here. All right, so here's what I've got so far. I have xy lambda. I know that lambda can be 1 or negative 1. Okay, so let's take a look at this case. What if lambda's 1? If lambda's 1, then come back over here. Well, you can do it right here, actually. If lambda's 1, then what's x? 2. And if lambda's 1 here, y is 3. So we get 2, 3, right? If lambda's negative 1, then x is negative 2, and y is negative 3. See how that all falls out real nice? But this was all under the assumption that lambda wasn't 0. All right, I think we've exhausted this. So we've got 2 points to look at so far. But now we need to take the other consideration. If lambda is 0, then what can you tell me? So we have to start all the way back at the beginning, right here. If lambda is 0, what? Yeah, then equation 1 makes no sense, right? There's no way you can solve this equation. If lambda is 0, right? If lambda is 0, then equation 1 becomes 2 equals 0, which as far as I'm concerned is still not true. Yes? And therefore, right now, this tells you lambda can't be 0. If you can't get the first equation to work, you don't need to look at any more. So that's it. We're done. We're done. But this has to be there, okay? This has to be there. You have to think through the step because it doesn't always work out that it just doesn't work. Sometimes you might get answers from this. All right, so now I'm ready. Pardon? Yeah. Yeah, because it's a plane and the circle went up there, it makes sense that we should only have 2, right? All right, so here we go. Now we actually find the max and mins. So we want to do f of 2, 3 and f of negative 2, negative 3. And let's see what we get. So f of 2, 3 into the original function, 2 here, 3 here. So 8 and 16. Am I doing that right? 8 and 16 is 24, and then if we do negatives, it'll be negative 24. So the maximum value of this function constrained to this, did I mess it up? Okay, whatever. What did I say? 4 times 2 is 8 plus 18. Yeah, I don't know. I told you all arithmetic, I just don't, something about my brain, once it gets to arithmetic, it truly doesn't care anymore. I don't know what it is. All right. What do you think? Algebra in there was just a little bit different, right? Okay. And that's the thing about these problems. The algebra in each one is just a little bit different. So there's no like cookie cutter way you do all of these, other than you got 3 equations set up in the beginning. Like, that's universal. Other than that, though, the algebra to get to the answer is different. So here's the picture of what we just did. We took this plane. We took that plane right there, okay? And we restricted it to that circle. We plugged those points from the circle into the plane, which gave us this ellipse-looking thing. And then we can take all that out of there. And basically we found those 2 points. This one right here, 20 whatever it was, and negative 20 whatever it was. Yes? Okay. Next one. Now the functions start getting more interesting, and now we're not looking at a circle anymore, right? X cubed plus y cubed equals 16. Our surface that we're trying to find the max and min of is like an exponential function. Let's go for it. First thing I need is, should I write it or can I just, do you want me to write it or you want to take the derivative now? It's up to you. I'll write it. Partial of f with respect to x must equal lambda partial of g with respect to x. Second equation, partial of f with respect to y equals lambda partial g with respect to y. Third equation, g of xy must equal k. All right, what is that partial, that first one over there? Be careful on that. Chain rule. What's the derivative of e to the xy?
Y dx.
Yeah, it's itself, e to the xy, but then you have to take derivative of what's up in the exponent with respect to x, which would just be y. So this is going to be y e to the xy equals lambda, and then what's the partial of g with respect to x? 3x squared. Now I realize that you could put this constant out in front of lambda, and I could have been doing that like this whole time, but I just always keep them separate when I take my first derivative, you know, just the first time through. I can always clean it up later. All right, partial of f with respect to y is x e to the xy equals lambda times 3y squared. So they're similar, but they're different, aren't they? And then the last one is just the constraint. So the constraint here is x squared plus y squared, or y, sorry, x cubed plus y cubed. You know what I'm saying. All right, now the algebra here. Yeah, this algebra doesn't look too great, does it? So like, you might be saying, okay, look, why don't I, why don't I solve for x here? Maybe you're thinking that. I'll solve for x here, I'll solve for y here, and then I'll plug them in here. Maybe that you're thinking like the same thing we just did. The problem is you can't solve for x here, because even though you can get x by itself here, x still appears here. So you can't have x in terms of itself, right?
Solve for x on the constraint equation.
Okay, if I solve for x on the constraint, then I'm going to have something with y in it, right?
Yeah.
And then you want to take that and plug that in here. Then you'll have lambda and y still. Maybe. Maybe.
You have it on in terms of y, and then the other one you have in terms of x's.
Yeah. Well, if you solve this for x, then you come in here, replace your x's with that. Now just think about how ugly that would be, though, right? 16, this would be 16 minus y cubed. No, it would be cube root. Sorry, right? Cube root. Yeah, no. This is what you need. You need ideas. But see, you see how that idea? I'm like, yes, we could do that, but do we want to do that? So, any other ideas before I show you? Yes.
Can we let x equal y?
Let it equal y? If x equals y, then you'll be able to solve that, right?
Right, and then be able to plug it in.
And then plug in. So that would potentially give you a solution, but would it be the only one? right? So that might work, but is that the only solution we have? So there you're kind of like forcing it to happen. You're saying, well, I'm going to let x be y, but that's not necessarily going to be the only points where we actually get a max or min. All right, how about solving for lambda?
X and Y are both not 0.
If we solve for lambda, right? If I solve for lambda here, then I'm going to have to assume that x is not 0. And if I solve for lambda here, I'm going to have to assume that y is not 0.
So then-
Agreed?
Yeah, after we work that.
After we'd have to check
We
that.
have to check if X could be 0 or if Y could be 0.
Yeah. So this is where we have to start to really keep track of what we're doing, because if we ever do something algebraically that eliminates like something being 0 or something, we have to then go back and look at that. So I'm going to do something here that I just think is kind of cool. I mean, at the end of the day, there's other ways to get to this, but just look at this real quick. You see this expression right here, y e to the xy is almost this expression, x e to the xy. The only difference is the x and the y here. So watch what I'm going to do. I'm going to multiply this by x and that by x. All right? And I'm going to multiply this by y and that by y. Now, don't write that down, okay? But do y'all see what would happen if I did that? Do you see that the left sides of these equations would be identical now? And if these are identical, then I can set these two equal to one another. Couldn't I? All right, that's what I'm about to do. But there's going to be some conditional statements that I make here. Because we know that algebraically, you are allowed to multiply both sides of an equation by anything, right? Except 0. You can't take an equation, multiply both sides by 0. That's equivalent to dividing both sides by 0. So I'm about to make a statement. If x and y, now let me do it this way. If x is not 0 and y is not 0, then what can I say? Let me go ahead and multiply the first equation. Equation 1 can be rewritten as xy e to the xy equals lambda times 3x cubed. So does everyone understand what I did there? I took this equation, I multiplied both sides by x, right? So equation 1 becomes that, and equation 2 becomes xy e to the xy equals what? Lambda times 3y cubed. So I took equation 2 and multiplied both sides by y. But I had to have the condition that x and y could not both be 0. Now, I can set equation 1 equal to equation 2. I can do that because the left sides are the same. So when I do that, I get lambda times 3x cubed must equal lambda times 3y cubed.
You could start by taking together both sides.
Take everything to one side? Can I kill the 3's? Can I just divide both sides by 3 right now? Just let's get rid of that. And then I move everything to one side. Lambda x cubed minus lambda y cubed must equal 0. And I can factor a lambda out. That gives me x cubed minus y cubed equals 0.
So either lambda is equal to 0 or x cubed minus y cubed is equal to 0.
Either lambda is 0 or x cubed minus y cubed equals 0. Right, so I've done some factoring here. Now, there's different ways to do this, but you could look at the left side as a difference of cubes. You could bring the y cubed over and then take the cube root on both sides. The thing is, because it's cubed, you don't have to worry about plus or minuses. That's the good thing. So we don't have like these multiple conditions. So solving that, I'll just trust that you could do this. This is just x is y, which turns out to be one of the cases, right? So as long as x and y aren't 0, as long